In this slide, we will talk about the conservation laws in engineering. There are two types of engineering problems. One is the time variable or transient computation, and the second one is the steady state or the computation where the time is not a variable. So this is, if we give an example for the time variable computation, not example but formulation of it, actually we have a change in this case. It can be time or something else, but usually time, and this change can be determined by increases minus decreases. And for example, for the falling parachutist example, we have the dv over dt equals mg minus cv over m, and here m is the increase, mg is the increases, and cv is the decreases. And the subtracting these terms from each other, we can find the change, which is dv over dt. So another way, if we don't have changes or the change is non-existent, then we will have zero change or no change, and that means the increases and the decreases must be in balance, so they are equal to each other, and this case is called steady state. And here we can say that change is zero. That means increases minus decreases is zero. Or we can say increases equals decreases. Here I would like to show some examples for the steady state computations. In example 1, on the left hand side, you can see a flow of 4-channel pipes. You can see that in pipe 1 there is a flow in of 100, and in pipe 2 there is a flow in of 80. In pipe 3 there is a flow out of 120, and in pipe 4 there is a flow out, and it is asked from us. So in this kind of problems, actually the flow getting inside will be equal to flow getting outside. That's why we can simply write that 100 plus 80, which are flow ins, equals to flow outs, which are 120, and plus pipe 4, let's say flow 4. So from here we can calculate flow 4 easily as 60. So there is a balance of the flow in and flow out, and because there is no change in time or in any other term, this means we have a steady state problem. And in the second example on the right hand side, you can see our falling parachutist example, and you know that for this one we had a change of the forces. The downward force and upward force had a change, had a different, as we showed in the previous slide. But in this case, we would like to say that, let's say we have a steady state condition and the net force is zero. That means that the difference of these values is zero. If we assume that Fd is Fu, then we will have dV over dt, the change is zero actually. That means mg minus cv over m is zero. In that case, so simply mg is cv, and we know that these are these values. Then we can simply have the result of v equals mg over c. If we isolate v here, we will have mg over c. And this can be solved to calculate the terminal velocity. That means that when the time is constant, we can simply find a terminal velocity. So let's say m is 68.1, c is 12.5 as in our example, and g is 9.81. We know that this is kilogram per second, and this is meter per second square. If we use this in the formulation, V is 68.1 times 9.18 over 12.5. From here, V is 53.44 meter per second. This velocity is obtained in the case of the steady state computation, and you can see you should remember this value from the numerical and analytical results at the bottom, where we said that if the time is at infinite, we will have this 53.44. That means that if we get closer to the infinity, the time becomes, or the air resistance and the downward force, gravity force difference becomes equivalent to each other, which leads us to an balance condition, and at that balance we will have this velocity eventually. So from the start point where we jump to the final point where we have a steady state condition, the velocity will increase gradually and will reach to this value and will be constant at this value. So we can easily find the maximum velocity using the steady state condition for the falling parachutist example. In this slide and the following slides, we will show some engineering areas that includes the conservation law. For example, in chemical engineering, you can see a reactor over here and reaction of the chemical components, and we actually use a conservation of mass here, and there is a mass balance. As you can see, the inputs are equivalent to outputs. So if we think that inputs are equal to outputs, that means a steady state problem. But if there is a change, inputs minus outputs gives a change, delta mass, and this becomes a transient computation, not the steady state. Similarly, in civil engineering, for example, also in mechanical engineering, in the statics class, we have seen that there are truss structures like these, and we use the conservation of momentum, or if it is steady state, we use the balance equations for the forces. So if there is a force balance, the forces in x direction, for example, or horizontal forces, the change is zero, and for the vertical forces also, the change is zero. And by using these, we can find if there is one unknown force, we can find it. And in this slide, also there is a mechanical engineering application. For example, for a machine, let's say an automotive suspension system, we can use the conservation of momentum and again the force balance. The upward force and downward force are equivalent to each other if there is a force balance and the change is zero. And if there is a change, then we can say the difference of the forces gives this equation m times a, and this is actually the second derivative of the position x, which gives the acceleration a. So F equals m times a over here. For the electrical engineering area as well, for circuits, we can use the conservation law. The conservation of charge, for example, the current balance, we can say that the total currents are equivalent to zero for each node. Also, conservation of energy for the voltage balance, for example, you can see here, the change also can be zero if it is steady state, as you can see here. So in different engineering areas, we can use the conservation law in a similar manner. If there is a change, it's a transient behavior. If there is no change, that means there is balance and it's a steady state behavior. So with this, we completed chapter 1 and we are at the end of chapter 1. So you can read chapter 1 in your book for further information and have more information about this topic. And thank you for listening. See you in the other class.